Okay, so in this video, we'll talk about how to calculate a battery electric vehicle range. So let's recap a typical structure of a BEV. So in a BEV, there is a vehicle which is trying to overcome resistances offered while it's moving on the road. So we'll talk about these resistances shortly. So let's say this is a vehicle, and I'm just drawing a top view and the power flow diagram. So there is a differential which is connected to the wheels, and this differential is kind of powered by a motor. Assuming there's no transmission, if there is a transmission, there could be a gear reduction between motor and differential. Then this motor, typically the motors in a BEV is AC machine, so it needs AC power input. So there is a inverter which gives out AC and takes in DC current or DC voltage from the battery. In addition, there will be some infotainment system available on the vehicle, which we can call it as auxiliary loads, and these are also kind of powered in some sense directly or indirectly by the main battery. There could be secondary battery as well, but the secondary battery will be eventually charged by the main battery. So just to simplify, we can assume just one battery, and this is the setup. So the range of the vehicle is a function of the battery capacity, and battery capacity is in the units of typically, let's say, ampere hour, and the battery energy is in the units of kilowatt hour. So to be able to estimate what would be the range of the vehicle, we need to first understand what are the losses which the battery needs to overcome, or where is the power delivered by the battery being distributed or lost to arrive at what the range would be, right? So let's understand first what are the losses, major losses in a vehicle. So starting off with a simple block diagram, let's assume there's a vehicle. This is a side view and it's moving with a velocity of v. So as it's moving, assuming there's still air, if there's wind blowing, then this relative speed can also become higher or lower depending upon wind direction. Assuming wind speed is 0, there will be some aerodynamic force acting, which is a function of this vehicle speed. It's a function of relative speed between wind and the vehicle body. So that's why we are calling it as a function of vehicle speed. Then there will be some backward force acting, which is known as rolling resistance, which is preventing the wheels from moving ahead. So this is another resistance. If the vehicle is moving not on a flat road but on a grade, then there will be some gradient force acting as well. And if the vehicle is not moving at a constant speed but accelerating, then there will be a pseudo force, we can call it the inertial force, Fi also, which the vehicle needs to overcome. So in a nutshell, these are the four forces. So we can classify at the wheels. Let's assume what is the force, that the total force. So it's a sum of rolling resistance, aerodynamic force, gradient force, and the inertial force. Inertial force includes the force required, or in other words, the force or torque required to accelerate all the inertias. So the vehicle might start from rest and it might accelerate, but the power comes from battery all the way to wheels. So the motor itself might be at 0 rpm initially, and to be able to reach certain rpm, which corresponds to vehicle speed based on the gear reduction, we need to move from 0 to n, right? And so the motor itself needs to accelerate, and similarly all the other components in between, like the drive shaft, differential, axles, etc., all of these needs to accelerate. So the effect of all these acceleration are kind of included in this Fi, which is inertial force. And this is the net force at the wheels. Now, um, assuming that this is known to us, and just a small breakdown of what these forces are. If you need more clarification, just put a comment and I can create a separate video on each of these in more detail. But to keep it short, FRR is, let's say, mu mg, where mu is or we can say CRR mg, coefficient of rolling resistance times mass of the vehicle times acceleration due to gravity. Fa, aerodynamic force, is half rho A CD V square, where rho is air density, A is frontal area which is exposed to the air, and CD is the coefficient of drag, and V is the relative velocity between wind and vehicle body. So it's the square of the relative velocity. The gradient forces can be mg sine theta. If there is a slope, of course, this would also be CRR mg cos theta. This would be mg sine theta. Fi is the m effective, which is inclusive of mass of the vehicle, static mass of the vehicle, or which we also call as GVW, plus the effect of all the inertias in the model. So it's a sum of these two. There is some complex relation, but we're calling it m effective times the acceleration of the vehicle, which is nothing but dv by dt. So these all four forces will compute the net force at the wheels. Once we know this force at the wheels, we can calculate torque at the wheels, which is nothing but force times the wheel radius. Force is in Newton, this is in meter, this would be Newton meter. Now once we know the torque at the wheels, we can get torque at the motor, which is equal to torque at the wheels divided by the final drive ratio. Final drive ratio is the ratio at the differential, FDR. Okay, so once we know this torque at the wheels, torque at the motor, then okay, so next is torque. Once we know the torque at motor, we can also similarly calculate the RPM of the motor. So there's a simple relation between vehicle speed and RPM. It depends on the gear ratio in between, and the relation is N is equals to 175 by 66. These numbers just came from unit conversion, times V in kmph times the total gear reduction, which is equal to the gear reduction in, if there is a transmission, times FDR times any other gear ratio between motor and the wheels, divided by the wheel radius. So this gives us velocity, this gives us RPM of the motor. So now we know Tm, we know the RPM of motor, torque and speed of motor. This will give us the efficiency of the motor. So motor cannot completely convert the electrical power coming from the battery or inverter into mechanical power without any losses. It's impossible, right? In a realistic world there will be some losses. So the this efficiency is generally a function of Tm and Nm, and once we know the efficiency, with torque and RPM we can calculate power of motor, and with the help of power and efficiency we can calculate what is the electrical power demanded by the motor from the battery. So, and this is nothing but it depends on whether we are charging or discharging, but assuming we are discharging the battery, so definitely will lose power. So battery will deliver, let's say, some energy PE, but the motor will give out some energy PM, and PM will be less than PE, and efficiency is less than 1. So basically PE is equals to PM by efficiency. So once we know the electrical power demanded by the motor for the given speed, now we can calculate the total battery power, which is equals to PE plus P auxiliary. Auxiliary is nothing but infotainment system on your vehicle, or it could be headlights, it's an indicator and so on. And now there are in BEVs there will also be, let's say, some GPS screens with some network or Wi-Fi options available. So yeah, all of these computes auxiliary, and then there will be AC loads as well, so which is also a part of auxiliary, let's say. So this is what we demand from the battery. Now once we know PV, and since we will also know what the SOC and resistance is at a given temperature of the battery. So with this information, instead of SOC we would know what is the OCV at the given SOC. So let us say we are at time equals to 0 and SOC is equals to 1, or SOC initial. So now our objective is to calculate what is the range of the vehicle. Now before we arrive at the range of the vehicle, we need to know what range actually means. So range is basically the amount of distance the vehicle can travel before it reaches a lower SOC threshold. Let's assume that the lower threshold is 0. So the amount of distance the vehicle can cover between SOC 1 to 0 is nothing but your range. So now in order to compute this range, what we need to do is at every time instance we need to find out what the current SOC is. So now to get to that, what we need is current and voltage of the battery. So there are very simple relation. PB is equals to V times I, and OCV equals to V plus IR. Now this is known. So this is known. PB is known from previous calculation, this one, and R0 is known So we have two equations and two unknowns, so we solve for v and I. So it will be a quadratic equation once you substitute one into the another. Once you get v and I, we use simple Coulomb counting. So Coulomb counting, what is Coulomb counting? Coulomb counting is simply SOC equals to SOC at time t is equals to SOC I. Now let's make a convention. I positive is for discharge and negative is for charge. So when you are discharging, your SOC should decrease, right? So the SOCI minus integral of I dt divided by Q. Q is nothing but the capacity of the battery, which we discussed initially, this one. So whatever ampere hour of capacity the battery has, you find the integral in ampere hour divided by the total capacity in ampere hour. Make sure the unit is consistent. If you use ampere second for numerator, use ampere second for denominator as well. So once you calculate this, you get SOCT, and then basically you eventually will arrive at the total kilometers. So in case the vehicle speed itself is changing, this concept of SOC can be very useful, where you can use Excel or some simple simulation tools to integrate over time how the current varies for a given drive cycle, and calculate once you and basically stop counting once you reach the lower SOC limit, and that's what your range would be. Calculate, so just integrate velocity to get distance, and that's what the point where you reach the lower SOC in, the integral of velocity over time at that instance is nothing but your range in kilometers. But in a simplified case where let's assume we are traveling at a constant speed of let's say 10 kmph, that means we cover 10 kilometer in 1 hour, right? And let's assume that the energy of the battery is 100 kilowatt hour. Now this is the total energy stored in the battery, and let us say that the PB value which came up from the previous calculations is around 10 kilowatt, constant 10 kilowatt, because assuming there's nothing changing, even the speed is fixed, everything else is fixed, no road gradient and no change in wind velocity, ideal scenario. So in that case, the power of the battery is 10 kilowatt constant. So that means it consumes 10 kilowatt hour in 1 hour. We're just doing integral. So E is nothing but E is equals to integral of PB. Okay, over time. So with this, what we eventually need is range. Range is nothing but the amount of distance you travel in 1 hour divided by the, in other words, it's, if you do just a unit balance, so it could be kilowatt hour, that's the total energy of the battery, divided by the kilowatt hour consumed per kilometer. If we do this, we get range. So our total kilowatt hour is 100, and the the vehicle uses 10 kilowatt hour to cover 10 kilometers, because both are for 1 hour duration. So we can relate these two. So that means the efficiency of the vehicle is 10 kilowatt hour per kilometer, 1 kilowatt hour per kilometer. So that gives us 100 kilometer of range. So that's how the range can be calculated for simple constant speed scenarios. And in case of
I'm not quite sure how to help.
And in case of a varying speed scenario, as we discussed, you can use this SOC based approach. So just in one column put the vehicle speed versus time, and then gradually build up to calculate SOC. Starting off, so just to recap, we started off with calculating the force at the wheels, which was a sum of four forces: aerodynamic, rolling resistance, gradient force, inertial force. Then we calculate torque at the wheels using radius. Then we calculated torque at motor using the gear ratios or final drive ratios. Then using and parallelly we also computed from vehicle speed, we calculated the motor speed using again the gear ratios in between and radius of the wheel. So once we know these two, we know what the efficiency is, we know what the power demand is, which gives us the electrical power. Then with the help of auxiliary, we calculate the battery power consumption, and then with battery power along with OCV and R naught, we can calculate V and I, and with the help of current eventually we can, and capacity, we can calculate the SOC. And then the way SOC decreases, starting from 1 to a lower threshold which could be even 10%. So you stop here, and in the meantime you also parallelly can plot how the distance increases, and the value which corresponds to this point is nothing but your range. So this is how you calculate range of a BEV. Hope that was helpful. Thanks for watching, and would love to hear your questions, comments in the comment section. See you in the next one.